Hey everyone, I guess it's probably time to start the course. Before I start the course, for this particular session of the course, I just wanted to say the aim of today's session is really to get you guys to run things on Archer, to specifically run LAMMPS on Archer. And as I'm sure you're aware, there's been some recent issues with Archer. Archer came back up last week, at the end of last week, I think Thursday, about midday. And since it's come back up, because the issues were security related, there's been new ways of logging into Archer, so there's new security things that you need to do. Unfortunately, because today is a bank holiday, I think one of you's already pointed that out, most of the people that work on Archer are either on holiday or not working on Archer today, which means that for anything like getting new login codes and things like that, it'll be a bit difficult. So hopefully you've all been able to log into Archer already or to update your Archer accounts at the end of last week. If not, they're unlikely to be they're not likely to be approved until probably at the earliest tomorrow. And if you're not able to log into Archer, you can still do some of the work here. You'll need to reduce the sizes if you want to run it on your local computer, but it won't be as simple to do, and you guys will need to do a bit more work. So if there's enough people who aren't able to access Archer today, what we're considering doing is maybe running another one of these sessions or having a 1 hour question and answer session in maybe 2 weeks, maybe a month's time. And during that session, like between this session and that session, you guys can go away and make sure you can access Archer and maybe run some of the exercises and come to that session with specifically the questions where you got stuck for the exercises. I'll go through all of the exercises at the start of this just so that everyone knows what the rough idea of them is and where to find them. Sorry, I just need to that page. There we go. There we go. Yeah, so I'll make sure to put links to everything, or make sure that you guys have the links for everything. Not what I wanted to click. That's what I wanted to click. Boom, and there we go. There we are. Hopefully you're seeing the slide I've got up for this thing. So really this lecture, this session is really an exercise session. It's really to help you guys try to play LAMMPS, because so far you've done an awful lot of listening to me talk about LAMMPS, maybe even watching me compile LAMMPS. If you stayed through that, thank you. But definitely not the most exciting thing and not the most useful thing. So this session really is meant to get you on Archer, running LAMMPS on Archer. And sure, it's only test systems, but some of them, you know, I've tried to make them at least somewhat physically relevant, or at least one of them is anyways, and still at the same time teach as much as I can about generally how to run simulations smartly and efficiently and things like that. As always, we've got this slide for if you want to reuse the material, you're more than welcome to, but please, you know, don't profit from it, and make sure to mention that you got it from here. We'd appreciate it. And lastly, I wanted to highlight at the start of this, because obviously everyone's now going to go into exercises and go at their own pace. If you guys want a certificate of attendance to show that you have attended the course, basically in the day one material, there's an input file called in.lj_certification, and it's exactly the same code as was run throughout the first day of the course. And to get a certification, what I'd like you all to do is to take that code from the first day of the course and modify it. That code was running at number of particles, volume, and temperature, and I'd like you to change it so that it's running at fixed number of particles, pressure, and temperature. Once you've done that simulation run, send the log file to training@epcc.ed.ac.uk, and I'll look at the log file. Provided you've done the right things, you will then get the certification for, a degree of certification that you've attended this course. So that's the thing I really wanted to not forget to mention. Next bit, let me swap screens to this. Yep. Next thing I wanted to mention is if you go on archer2.ac.uk and then click, this is quite small for you guys, let's make that bigger. Then click on training. I think it's still in training, though it might eventually end up on upcoming training. There is here the LAMMPS Online course. If you click there, that has a link to all the course material, including the blurb and things like that. Specifically at the bottom, there is course material, which gets you to the course GitLab page. This is the course GitLab page, and you can either git clone this page to get all of the information that you want, or I've also included all of the information on Archer in a shared directory. All of the stuff that we're going to go through today is in day 3 exercises class. And namely, there's 4 exercises. I'll quickly run you through them, and the order in which I think you should run them, though obviously please go at your own pace. If you're aware you know an answer already, don't spend time finding out an answer you already know. Just go on to the next one and play around with it. But I've tried to sort of do a number of things with these exercises. The first exercise is just performance testing. It's to give you an idea of, basically Archer is a huge machine, and this is probably the best exercise to do if you just want to run as large a system as you can on a large machine. This is also going to help you realize how sometimes you can accidentally be inefficient by putting not enough particles in your simulation and then running it on too many nodes and things like that. Definitely so far in this course, we have been running way too small or the number of particles we've been using has been way too small. And that means that our simulations have been inefficient. However, that doesn't mean necessarily that our simulations take a long time to run. It just means that we're not getting as much as we possibly could from our processors. So there's always that to take into account. All of this is done in exercise 1, which is about performance testing. The other thing that exercise 1 will do is the way that you get information for performance testing is by looking at all of the output data at the end of a LAMMPS log file. So after you get all of your thermodynamics outputs, at the end there's a bunch of information about how much time spent on different processes. This really delves into that in a relatively deep fashion, or I've tried to. I mean, it skims the top, frankly, because this is not a long exercise, but it goes more in depth, I think, than the lectures have previously. The next problem that I've set is on domain decomposition. That doesn't come out very well, actually. Domain decomposition. That's essentially, here we'll be looking at how LAMMPS splits up the simulation box. We mentioned this in the second session. But how LAMMPS splits up the simulation box, and specifically, we'll be looking at a system where splitting the simulation box in the quote-unquote usual LAMMPS fashion doesn't work very well, and look at how we can be smarter about how we distribute our box amongst the processors to really get the best performance that we can out of this. It's still heavily performance-based, but it's a completely different idea. The third exercise is looking at the electrostatics effect. So far, we've only looked at very short-range Lennard-Jones interactions. In the electrostatic exercise, we'll add a couple of charges to our particles. I mean, most physical systems, definitely most atomistic physical systems, will have charges, and we've not even looked at how to consider them yet. this entire exercise tries to address that, to show how you can add charges, what's the cost of adding charges, what the benefits of adding charges, and how you can go about doing that cleverly. While I focused here on electrostatics, the general idea and the principles that we're using can be used for a lot of longer ranged interactions, i.e. interactions that are still significant, particle-particle interactions that are still significant at distances greater than 1 box length. And the last exercise is to look at water evaporation. And essentially this one I've tried to, like all of the other 3 exercises, have relatively theoretical systems, or, you know, unless you're really interested in how argon gas moves around, you're not going to simulate Lennard-Jones particles very often, probably. They're super useful, and you can still get some good physics and good research done with Lennard-Jones systems, but definitely it's not the hot thing anymore and hasn't been quite as in use as more realistic systems for at least, I don't know, definitely the last 20 years, probably longer. So I thought, you know, let's try one simulation or one set of simulations where we're looking at a real problem. And in this case, we're starting with a simulation of water at a temperature of 275 Kelvin, so just about water, liquid. And you'll then increase the temperature of that water up to 450 Kelvin and look at the thermodynamic properties. I'm sure you can all guess what's going to happen to your water, but it's still nice. Like, you know, this is a nice way to show a lot of the, you know, to show a lot of the thermodynamics that you can get out of lamps easily. And while water might be one that's been done an awful lot of times, this will still get you some cool results, some cool actual physical results. So I hope that all makes sense. I will very briefly show you guys where you can get all of this on Archer. And then I will also ask, I mentioned, I remember that last week there were a number of people, or 2 weeks ago, there were a number of people who were interested in how to create and pack simulation boxes when you're not just doing it in lamps. So I'm going to quickly do a poll and then show you guys how to get onto Archer, to get the information, the input files on Archer. But yeah, so if enough people are interested in how to pack a simulation system, I'm happy to briefly show that. It'll be a relatively simple example, but that will be me going through things because a lot of the softwares that I use are not necessarily on, or pretty sure are not on Archer. So this will be a bit hand-woven, and bear in mind that this is definitely how I would go about preparing my systems. There's loads of other ways of doing this. It's just one, well, my personal method of doing that. So let's move to this one. Cool. Can you guys see this okay? Yep, brilliant. Thanks for that. So all of the information for today's course, these are my home directories, there we go. All of the information for today's course on Archer can be found in /work /shared, /work /y14 shared LAMMPS A3 materials. This is, let's maybe copy it to here and do that. This is just a copy paste essentially of the stuff on the Git page. So you can also git clone if you'd rather do that, or wget, I guess you can probably use as well. Here's a copy of what I've just typed into Archer if you guys want to do that as well. If you go into day 3 materials, you'll notice that there's a number of directories. As I said, they're exactly the same names as how I named them at the start of this session. So performance test is in one performance test, domain decomposition is in 2_ domain decomposition, etc., etc. If you go to performance test, there are 2 directories, one to test how particle numbers can be changed. And the other one is for if you want to run on multiple processors. In every single one of these directories, there is a README. If you look at a README, that just is exactly the same page as would be on the GitLab. It's probably nicer to look at on the GitLab, but it's also there as well. And if you go into any directory where every directory here has an input file, so in this case, in.atom numbers, an instruction file, which will give you instructions for how to run your simulations. Here, I appear to have forgotten to add an Archer submission script, but you should be able to copy an Archer submission script from a previous day. Oh, no, apparently this one has a submission script. So let's just quickly, here we go, it's the same submission script. Cool. If you look at the LAMMPS submission script, yeah, it just runs in.lj. And if you go into different directories, the decomposition again has your LAMMPS input script and your instruction file. Cool. Cool. So I'm getting a question. Someone's asking me about a specific system that they're interested in packing, and said that they've got an XYZ file. That you have an XYZ file is awesome. The method that I'm about to show you for packing systems works really well if you've got an XYZ file. If you are so for those of you who aren't interested at all in how to pack your systems, feel free to mute me for the next probably 10-15 minutes and carry on with the exercises. For everyone who is interested, please give me 1 second because this is completely off the cuff, so I'd like to make something slightly, yeah, that looks good. Make something slightly nicer looking than what it currently is. One thing I forgot to mention, one thing I really want to stress is if you have any questions about the exercises, please post them in the chat either to me privately or to the general chat, and I will answer them as we go. The entire purpose of this session is really for you guys to have a play around with these systems. So I'll be doing an awful lot less talking than the last couple of times. That's what I want, and I want that one. Actually, let's go back to here first. So the way that I usually pack my systems, if it's not just a simple Lennard-Jones fluid or some simple fluid, is I use a program called PackMol. PackMol is free to use as long as you're using it for a personal thing. You can just Google PathMol. It's the very first thing that comes up, and it's quite literally a system for randomly packing a box with certain criteria. You can have criteria like how much overlap you can have between particles, how little overlap you can have between particles, all sorts of things like that. They have, if you want to download it, you can go to download. They usually ask you to fill in the form so that they have an idea of who's using what, but I'm pretty sure you can download, yeah, you can also download from this site without registering. Whatever you'd rather. We do not work for or in any way associated with PathMol, so issues with PathMol are probably best dealt with by sending them an email than us. They've also got a great user guide with loads of examples on exactly what you want to do, what you can do with PathMol. How to install, some common issues that you can have, but they've also got a great thing of the constraints. The constraints are really what you're after. The constraints are what you're telling PathMol you are happy with it to do. So do you want your particles to be in a cube? Do you want them to be in a rhombus? Do you want them to be in a sphere? You can define all of that. And this tells you everything. So for instance, number 2, inside a cube, here's how you can define your cube. Outside a cube, here's how you can do it, etc., etc. I've just copied across the PathMol files into here, and these aren't available. I can make them available if you guys want, but I imagine that actually it's probably going to be easier for you guys to just look on the PathMol website for this sort of thing. But I have 4 things in this directory. 3 of them are interesting. The first one is water.xyz. Water.xyz is a simple XYZ file that defines one water particle. It defines where the oxygen is and where the hydrogens are in relation to that oxygen. If I VMD water.xyz and show you guys the VMD window, there we go, share. There we have a water. It's lovely in all of its watery goodness. That's the one. Yep. So a water molecule. The next one we have is I've called it xyz.pathmol.imp. You can call your pathmol input file whatever you want. I call them that because otherwise I go insane. As you can see, this is completely unprepared, and I don't have. Well, I'll show both actually. Yeah. So what is my? This is my pathmol input file. This is the thing that I'm going to send into pathmol to path my system. And the first thing I define is a tolerance. I'm saying I want my particles to have this amount of tolerance, i.e. this amount of space around them from memory. The second thing is output. I am simply naming my output file. In this case, I want my output file to be called pathwater.xyz. File type XYZ, because I'm using an XYZ. I'm pretty sure that pathmol also runs with PDBs and a couple of other types of simulation boxes. Other types of simulation files. But in this case, we're running an XYZ. And then for every XYZ file that you want, you name that XYZ file and say what you want to do with it. So in this case, the first XYZ file that I'm adding here is a file called water.xyz. I want whatever is in that file to be called 1,000 times, and I want all of this to be inside a box which starts on 1, 1, 1 and ends on 30, 30, 30. So I've defined a box which is 1 by 30 by 1 by 30 by 1 by 30. So 29 by 29 by 29. In this case, it's a cube. Another thing I could have done is instead could have done inside cube and done 1, 1, 1, 30, and that just defines that all of the other, all of the maximum points are 30. The because I'm just packing water in this one, this is a relatively boring example, but if I wanted, one of the questions I get is the added water, is the added water orientation random? Yes, the added water orientation is completely random. It is not necessarily physical. So you can, I mean, you'll struggle to pack it, but you can definitely pack a system at a volume where water should be crystalline, and it will not give you a crystalline output. The outputs are, I think for an XYZ file, the outputs are in angstroms, but I'm not certain about that one. I'll look at this when I'm through with the explanation. Sorry about that. So you define your first structure, and if you wanted to, you could then define another structure. So if you had, say, I don't know, a structure called, I don't in this case, but you could have structure protein. You want one of those. You want it inside a cube, which is, I don't know, 10 by 10 by 10, and then 20. And then in that case, you probably don't want, let's write cube properly. You don't want your water to be in that same place. So you go 10, you say that your water shouldn't be in a cube, 10 by 10 by 10, 20. And then you run and structure. You can then run that into PackMol, and PackMol would be able to, would try to pack everything as best it could. Sometimes, obviously, if you're trying to pack too much and not enough room, it's going to fail. That's how you write your input for PackMol. Let's comment that out, but I'll leave that for a sec. Once you do that, you can just run your PackMol executable. You will have had to compile it, but there's compilation instructions on the PackMol website. You run your PackMol executable, input your PackMol file. So run your PackMol executable, input your PackMol file, and hey, look at that. There's now a file called packwater.xyz. pi packwater.xyz. And that just gives you, there's 3,000 particles total, which means there's 1,000 water particles. And if we vmd packwater, 1 second. vmd packwater, there we go. We have 1,000 water particles inside a box, which is 30 by 30 by 30. And you will notice if I zoom in, the water particle orientations are completely random, and the water particles have been added such that there is at least 2.7 distance units, if I remember tolerance correctly. By the way, there is a bit of a caveat there, but 2.7 distance units between every particle. I think that's what tolerance does. Let me Google that. Yeah, so the default behavior is that all atoms will be distant to each other at the final structure, at least the distance defined by the tolerance parameter. And all units are in angstroms. To answer the question about whether units are in angstroms, what the units are. Yeah, that's fine. I don't know why I just exited that. Anyways, I know, I remember now. Did I show the right one? Yeah, cool. Sorry. So we now have our packed water, but this is a packed water XYZ file. It's still not a legitimate LAMMPS input. And the way that I usually go about making my LAMMPS input, oh, sorry, before we go into LAMMPS input, one last thing I wanted to show was if we have outside that box and maybe increase that to, I don't know, stupid amounts because I don't want it to crash. There we go. And look at the VMD. There we go. So now if we look at our simulation box, there is a box within our box which has absolutely no particles. And that box within our box without any particles in it, I don't know if you can see it very well, but it's definitely there. That box within a box starts at position 10, 10, 10, and is a box that goes 10 to 20 by 10 to 20 by 10 to 20. So that's how you can have things in only certain regions of your box. You can also do spheres, you can do ellipses, you can do all sorts of shapes through PathMol. Let's close that and let's go back on shell. So we now have our simulation box. I'll a little more acceptable. Oh, no, the last one. We now have our simulation box, but we're not done yet because that's an appropriate input for LAMMPS. LAMMPS asks for very specific input files, so we still need to do one step of preparation. So far, we've quite literally just multiplied our waters and placed them in the right places. Bear in mind that everything that I've done here for packing your system, it gets you a standard XYZ file, which means that if you've got other simulation software that's happy with XYZ file, or if you'd gone the PDB route, if you've got other simulation software that's happy with whatever PDB files, this is a legitimate way of creating a desired XYZ or PDB file. With LAMMPS, however, there's still another step, and that other step is to prepare the LAMMPS input file. And this one, LAMMPS data file. This one takes a bit more step, and the thing I tend to use for this is a VMD extension. The VMD extension is called Topo Tools. Topo Tools is again Googleable. Sorry, 1 second, I'm getting a question. Yeah, so someone is asking whether I can create a .tar file for all of the day's materials to make it easier to copy things. Yeah, I can totally do that. I'll do that either when everyone's starting on the questions or when I'm done with the current PathMol things. Sorry. So Topo Tools. Topo Tools is a tool set for VMD. And I think, again, just Google Topo Tools. Topo Tools is a toolset for VMD, which is developed by Axel Kollmeyer. Axel Kollmeyer is one of the developers of LAMMPS. And honestly, this isn't the best document place ever, but everything about Topo Tools, yeah, Topo Tools documentation is here, which explains how to do loads of different things. Basically, Tools allows you to, in VMD, set a bunch of different properties for the atoms that you have within VMD. So you can choose a certain number of atoms by name or by type or by position and give them certain properties. You can change their names, you can change their charges, you can change their radii. That can be really useful if you want to have realistic simulation pictures and things like that. So I tend to use Topo Tools, and because I am quite lazy about when it comes to the things, this one, wrong one. Because I am quite lazy when it comes to these sorts of things, I just have a Topo Tools input, and I'll just talk you through it. So the system has two, because we've just got water packed into a box, our system just has two species of atoms. We've got oxygens and hydrogens. And what this file does is, here I'm setting a dummy variable called select cell H. And that cell H is a dummy variable that stores all of the atoms, atom select, from the top of the file that have a name O. So you start at the very top of our XYZ file, and for every atom named O, they are added to this dummy group. Then for every atom in this dummy group, I'm going to set the mass to be 15.994, i.e. the mass of oxygen. I'm also going to set the charge as being minus 1.484, set the element as being oxygen, and set the radius as being 1.2. Then I'm going to do exactly the same because cell H is a dummy variable and these are set as we go. I'm going to do exactly the same things for all of my hydrogens, except with different properties for mass, charge, radius, etc. Once this is all done, I'm going to run this thing, and this is this command mul bond recalc all is essentially, if you've packed things a bit too closely, VMD has a tendency to look for bonds where there aren't any. This command lets you, once you've defined all your particle radii, tell VMD, okay, look through everything again with the parameters I've given you, and make sure that those bonds are actually realistic. And VMD will do that, and if you've got densely packed systems, that's a nice way of losing or of getting rid of a number of bonds that don't exist. Then retype bonds is a topo-tool command that just lets you it just goes through all of your things and checks all of the different types of bonds that you have. In this case, we're just going to have OH bonds because it's water. Num bonds is for every type of bond, give them a number. So if we had more than one type of bond, the first bond that it comes across would be called number 1, and the second would be number 2, etc., etc. Guess angles is guess how many different types of angles there are. Guess dihedrals is guess how many different types of dihedrals there are. I skipped out num-bond types. My apologies. Num-bond types is find the different number of bonds types you have. Yeah. So topo num-bonds gives you the total number of bonds that you have. So in our case, we've got 1,000 water molecules. Each molecule has 2 bonds, i.e. 2 OH bonds. So topo num-bonds will get you an output of 2,000. Whereas topo num-bond types will get you an output of 1 because there is only one type of bond, the OH bond. Guess angles, guess dihedrals, I've just said. And then finally, you've got topo write lamps data, tip4p.in, which is a stupid name thing to call this because this is tip3p water from the looks of it. 3p. .in. And let's call it so write lamps data is quite literally a command to write out your data file for lamps. Once you've done that, so again, as I said, I'm quite lazy when it comes to this, so I just tend to copy paste, copy VMD, paste, and there I've done everything. So as soon as you do a topo thing, it tells you, oh, you're using topo. Please cite topo tools. Here's how you cite it. So our first thing was retype bonds 0, number of bonds 2,000 as expected, types of bonds 1 as expected. Then it writes the LAMMPS info files, and once that's done, you connected VMD, and you've got a new file in our case called tip3p.data. If you look at tip3p.data, that's the LAMMP input file. Top line just tells you it's been generated by topo tools, and it tells you this file contains 3,000 atoms, 2,000 bonds, 1,000 angles. You have 0 dihedrals, 0 improper angles. There are 2 atom types. There is 1 bond type, 1 angle type, no dihedral types, no improper types. And then here it makes a terrible guess at the box length. That's because I've put in an XYZ file. From memory, if you use a PDB file, you'll get better results. However, you will still always need to change those boundaries. So I think ours went from 1 to 50. So we'll do 0 to 51.5. I'll explain why in a sec. Here we go. After this, here you get a couple of commented lines where you can, if you want, define your LAMMPS pair styles here. Here you get a couple of further commented lines where you can, if you want, define your bond coefficients. Here you get a couple of comments where you can, if you want, define your angle coefficients. You can also define your masses. It defines your masses for you because when, if you remember, one of the things that I defined for my particles was their mass. And then finally, for every atom, it gives you the atom position. So we know that atom number one, is a, let's see if I remember this. Atom number one is a type 2 atom, which is an oxygen, has a charge of -1.048 and is in position 18.417, la la la, 2833. And it says that for every single atom. As you go down, you see all of the atoms, and after we've gone through 3,000 of these, it will then start telling us the bond. And it tells us that the first bond is a bond between atom 1 and atom 2, second bond is between 1 and 3, and we keep going for long enough, and eventually we get to angles, and the angles just tells us angle 1 is an angle between atom 1, 2, 3, and angle 2 is at the center of that angle chain, which makes, is that right? Sorry, angle atom 1 is at the center of that chain. So the first angle goes from 2 via 1 to 3. So at this point, we've got our LAMMPS data file. And we can potentially run this using LAMMPS. I will now copy. So I've got an input file for water because, I was playing around with these. I have an input file for water, and this should hopefully run with the data file. Restart. Actually, to be fair, I can just comment that out and read data. I think I called it tip4p.data from memory. Tip4p, my apologies. Cool. And now, if I wanted to water, I'm able to run that input script with the input file that I've just used. So just to clarify what I've done, I have changed my LAMMPS input file so that I am reading a data file. So all of my starting particle positions are coming from the data file tip3p.data, the one that we've just created. A couple of other things that I've done is, like I knew that this was the correct file, right? But a couple of other things that I've done is I have named all of my pair coefficients. So I've done a number of things actually, but just to go back on the last couple of sessions, I'm running this set of parameters. So LJ cut, meaning a truncated Lennard-Jones interaction like we had before, with tip4p water, and I want long-range Coulombic interactions. Which is why I need to define a case space. In this case, it's PPPM, specially made for tip4p. If you're interested in case spaces, the electrostatics exercise is the place to go. Definitely. I've also defined my bond styles. I want harmonic bonds. My angle style, I want harmonic angles. And here I've defined my pair coefficients. And I've defined that particle 1 with particle 1 has a Lennard-Jones sigma and epsilon equal to 0. That's because in a lot of the tip styles of water, you pretend that your hydrogens are essentially effectively a point charge, and provided that your hydrogens are close enough to your oxygen particle, the diameter of your oxygen particle will encapsulate the diameter that your hydrogens would have, and you're more or less fine, which is why they've got a sigma and epsilon of 0. You also need to define that your interaction between your hydrogens and your waters is also 0, 0. And last, you can define that your water-water interactions are whatever that is. I've also defined my bond coefficients and my angle coefficients. All of these, except the middle line where I'm defining my water-hydrogen interactions, pairwise interactions, all of these I have instead put into my data file. So here, my hydrogens, I could have put instead, this one's easy to do, I should be able to do it off the top of my head. I could define my hydrogen as being 0.0. I'm not saying that for particle 1, interactions for particle 1 are 0.0, 0.0. And then for particle 2, if I remembered the water, it's whatever and whatever. So, and I can input all of this information within my data file and not have to put my pair coefficients within the LAMMPS input file, the thing that I run into LAMMPS. There's some advantages and disadvantages to both. I've never run systems that were so large that it was worth me doing that in the data file, but of course, if you've got 20 to 30 different atom types, each interacting, doing this in the data file rather than the LAMMPS input file is a lot more neat, and there's less, I mean, frankly, there's less stuff in your input file, which makes it easier to go through. That's it for the whistle-stop tour of how you can pack a LAMMPS data file. I hope you guys found it useful, and I will now let you guys get on with the exercises. If you have any question for the exercises, I will be here till 4:30, and I'm quite literally just here to answer questions. So it can be to do with the exercises, it can be to do with other things. I'm really here to help. Cool, hey again, everyone. So I'm gonna very quickly go through an overview of how to run the water evaporation exercise, because I've got at least one person who's wanting to see how that's done. If this is something that's of interest to you, please carry on listening. If you're not that interested, please feel free to just mute and carry on with the exercises. That's absolutely fine. However, before you mute, I wanted to quickly point out, give me 1 second. Sorry about that. I accidentally closed the wrong window. So I wanted to quickly share this page. First of all, if you now go on the course GitLab page in Day 3 exercises, water evaporation, I've now added in the data file prep directory all of the pathmol files with a quick README instructions for all of the things that I showed at the start of this session on how to pack a system using pathmol. And I've included all of the files that I use to do this. Possibly useful to some, I do not know, but it's there if you guys need it. So that's actually quite handy, because we will be we'll be doing the water exercise anyways, and The entire idea of the water exercise is, water evaporation exercise is, we're starting with a file that has a simulation restart file for a simulation that was run for 1 nanosecond at a temperature of 275K. I should also specify the simulation box contained 2,500 water particles. So, you know, somewhat big. And the idea for this exercise is to run your simulation at 275K and then slowly increase the temperature. Simulation, so from 275 to 300 to 325 to 350 to 375 all the way to 450, maybe even as high as 500 if you're feeling particularly, you know, up for it. And then look at some of the thermodynamic values that are output. So I have run this previously. Let me get a shell up. And, you know, I'll try not to close my collaborate window again. There we go. So here I'm on Archer, directory. Water evaporate. So here you start off with two files of interest. You've got your restart file, which is just a binary. It does let you pet. I'm not even going to bother. But yeah, you've got a restart file, which is just a binary, but it's a binary that has the end positions of all 2,500 times 3, so 7,500 separate atoms in the original simulation at the end of the 1 nanosecond run. And then we have our input file. Our input file is exactly the same as the one that I showed you today, but just as a reminder, what have we got? Well, we've got a set of variables at the top. I've tried to, for all of these exercises, have easy variables that you can switch on and off or change the number to, just to make it easier for you guys so that you don't end up having to spend like minutes, hours, whatever, looking for the correct commands. Because, you know, if you're going to use LAMMPS long-term for research, you'll end up doing that at some point anyways. You don't need to do it for your very first couple of simulations. So to do this exercise, there's really just two numbers you need to play with. The first one is the temperature. The temperature defines what your simulation's temperature is going to be for this run, i.e. for the one that you're preparing. And there's the last temperature, which defines the temperature of the run for which you've got a restart file, or for which you're going to use the restart file. Pressure is 1 atmosphere. Pressure of 1 atmosphere is usually sensible. Time step of 1 femtosecond. You can sometimes push it to 2. You can probably push it to 2 in the simulation, but you know, keeping it at 1 is usually not a bad move. The delay just defines how often or how rarely you want your thermodynamic outputs to be. At the moment, I want them every 100 femtoseconds. Fine, you can do it more if you want. The more you do it, the longer you'll spend writing input outputs, and also the larger your data file will be. The less you do it, the more likely you are to miss some interesting thermodynamic phenomenon, or in this case, because we'll be averaging over something which is more or less steady state. I mean, it is at certain points, but most of the time it is. You might get poorer averages. And then total time is just how long you want the simulation to run, in this case, 0.1 nanoseconds or 100,000 femtoseconds. We've got all of the LAMMPS inputs like we had before. Read restart tells you that you're reading a restart file called last step. Restart dot whatever the last temperature was, which is why you need to be careful when defining your last temperature. Reset time step to 0. That's just to mean that every simulation will run from time step equal to 0. If you don't have this step, the simulation, instead of starting at starting at time step 0 at the very start, it would instead start at whatever the time step was at the end of the restart of the simulation where the restart file was written. So in this case, because that restart file had been run for 1 nanosecond, it would start at time step 1 million, give or take. Pair coefficients, fine, defined. I've also defined a group, not drastically interesting. Neighbor command. Fix shake. Shake is a way of shake is one of a couple of methods to fix bonds. For this simulation, we're running with, but we are going to keep our water bonds fixed. We're going to keep them rigid. This is just one method of making sure that our water bonds are rigid, i.e. that the waters can't really fluctuate either. Neither the bond's lengths can fluctuate, nor the bond angle can fluctuate. And this is just to define that. Running Mose Hoover. We're using the fixed balance command. Some of you who've done exercise 2, you will have used the fixed balance command. We're using one in this simulation because we are going to be simulating water at temperatures between 275 K, which is what, like 2 degrees C, all the way to 450 K, which is 175 C. So at some point, we'd expect that our water would evaporate. When our water evaporates, our box size will increase. We're going to note under fixed NPT, so fixed pressure and temperature, meaning our box size can fluctuate, and our box volume, we expect, will increase at some point when the water starts to boil off. To make sure that each individual processor is running roughly or has roughly the same number of particles, we will rebalance the same box every so often to make sure that every processor has a box that is equal in particle number rather than equal in volume, and also to take into account this change in volume. We're outputting a radial distribution function, fine, and then we're just running the thing. Cool. The first simulation that you're asked to do is running this as is with runs. The first simulation that you're asked to do is run this as is. And I'm just going to be lazy actually. And I've already run these before because I kind of wanted to make sure that these exercises actually worked. So I've run all of these already, and as you can see, I've got a number of directories run at all of the temperatures, and I've run everything here. But the first step that you were asked to do is to run the simulation at 275K. So using restart.275 and using exactly the same input file as you had before. So in this case, temperature is 275, temperature is also 275. Cool. You run this simulation, and at the end of it, a couple of things will happen. First of all, you'll get a bunch of, you'll get an Archer output file called o.water, or you'll get whatever your job name was .o, and then the number is which number it was in the queuing system. You'll get an error file .e, and then what the number will be whatever was the number was in the queuing system. If you look at water.e, it's empty, meaning there was no error. That's usually good. And if you look at water_run.o, it's not output anything, but that is because in my submission directory, I have made sure that anything output to screen goes into a file called output.out. We'll get back to the submission script in a second that I wanted to show you guys, but for now, let's stay here. So we've got a file output.out which has everything that was printed to screen, and everything that was printed to that we would expect to normally be printed to screen is printed to screen in this file, including all of our thermodynamics data. Boom, 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 boom. And then at the end, we have all of the performance data that, for those of you who did any of questions 1, 2, or 3, will probably be, very familiar with by this point. Hopefully not too sick of them yet, but they're fascinating stuff. They're able to improve your performance and make sure that make sure that the correct parts are taking the correct amount of time. You can get some real speed ups. So yeah, there's that, and then the last bit we've got is a log file, log.lamps, which has most of the same info as before. That was step 1, and then step 2 was, okay, you take the restart file that's just been produced. The note, by the way, that the restart file in this directory now is not the same as the restart file I had originally. So 2 directories up is the restart file as you were given at the start. If I do a diff command, it tells me that the 2 files differ. They're binary, so it's not going to show me how they differ, but they are not the same binary. The reason for that is that in my LAMMPS, in the LAMMPS input script, the final line is write a restart called restart dot whatever your temperature is now. And we started with a restart called restart.275 because the original run was at 275, and we just run another simulation at 275 Kelvin. Which means that that restart file gets overwritten as one of the final steps, if not the final step, of the input script that we're running here. Bear that in mind, but it shouldn't be an issue past this. With that restart file, the idea is then copy that restart file across to a new directory, in this case 300K, change the LAMMPS input file so that it's now running for 300K. Namely, in this case, you're just increasing the temperature from 275 to 300, but the last temp remains at 275 for now. And run the simulation. You get all of the correct outputs, and then just keep doing that, 425, etc., etc. But from 325 onwards, you need to make sure that last step is increased so that you're using the restart file from 300K rather than 325, and you're running at 325. But overall, it's just doing that a number of times at a number of different temperatures to, I don't want to say slowly increase the temperature, but relatively slowly increase the temperature, or as relatively slowly increase the temperature as you can when you're, increasing the temperature something by 175 Kelvin in, how many files is that? 8, so 0.8 nanoseconds, I guess speed is all relative. 2, 3, 4, 5, 6, 7, 8. Yeah, so you're increasing by 175 in 8 nanoseconds. That's a fair amount of, that's a lot of heat going in quite quickly. There is a trick to doing this quickly on Archer. This is not true of every. This is not true of every script, but you definitely can on Archer have at the end of a submission script, provided that you've got your input files correctly set out and everything, and be very careful with this, by the way, because if you mess something up down the line, you can get stuck in an iterative loop, which you don't want to do. But it is possible on Archer to, as part of an input script, submit another. As part of an Archer submission script, you can submit another submission script. So just to have this running in the background while I was doing other stuff, I basically had my script set up so that once 275 is finished, it copies the correct restart file to the correct directory, moves into that correct directory, submits the new Archer submission script. And in the very last directory, to make sure that this doesn't go on forever, because you don't want this forever, because that can be quite expensive quite quickly, I've made sure not to add that. So This is a trick that you can use, but be very careful with. Because if you do end up relaunching the same job over and over and over and over again, your budget, which at the moment we have a shared budget, your budget will decrease quickly and painfully. Yeah, so once you've run everything, the entire idea of that exercise is to have a look at the average values for everything. And again, because I'm lazy, I've written a Fortran code to output the average values from all of the files and plonk them in a folder called output.1atmosphere. There we go. Still visible, I think, yeah. And yeah, so for all of my runs, here's what we've got. I've not named the columns because, yeah. We've got temperature, that's going to be E total probably. Is it E total? I don't know. Okay, look at lamps. Here. Hey, it was total energy. Here we go. So temperature, total energy, the reduced kinetic energy, so the kinetic energy per water molecule as opposed to the total kinetic energy, the reduced enthalpy, so the enthalpy per water molecule as opposed to over everything, the volume, the length of one box, and the pressure. You'll notice that the pressure fluctuates. Average pressure is meant to be around 1. It goes up and down a bit. That can happen sometimes, especially with these effects. Two things for this. The first one is pressure is usually hard to get to stabilize. And we are increasing temperatures quite quickly and seeing quite dramatic effects in how the system acts. That can lead to high fluctuations in pressure. For instance, at 325K, quite close to melting point, we've got a huge pressure as our thing is trying to melt, or at least starting to consider melting. It's a bit low after, yeah, no, that's okay. And also you can get negative pressures. That's just, sometimes you get those. You can get more accurate pressures by playing your barostat. In the order. You can play around with, here I've got a barostat, which I fixed at every 30 time steps, I want the average to be 1. That's one way of fixing it. The other way of fixing it, which is not feasible for this course because it would have taken you guys ages to run these simulations. The other way to fix it is usually the longer you run your simulation, the more your pressure will stabilize. When I say the longer, I mean like you probably want, I don't know, half a nanosecond to a nanosecond of just equilibration before even bothering with your run. But I didn't want you guys to spend ages waiting for runs to happen. I mean, already the early runs take about 10 minutes, and I didn't want that to be longer. We've got all of that. One thing that I'm sure you'll notice, and which is hopefully expected, is the volume increases dramatically suddenly as you increase the temperature. I will use everyone's favorite GNU plot to emphasize that. And let's get GNU plot up. Oh, nope, 7 is pressure. Volume. That looks like volume 3. Is that volume? That looks like an awful lot of volume to start off with. No, that's right. Yeah, that's volume. Yeah, so no, that's not volume. What am I saying? Sorry. Okay. This one is volume. Cool. What do we get from the volume? Actually, probably worth log scaling. Look. Ooh, let me do this. Technical difficulties. There we go. That looks a bit better. So bear in mind, this is a log scale. At least it's a log linear scale, just to emphasize the point. But this is the volume of your simulation box. And what does your volume do? Well, it's roughly steady up until about 325 Kelvin. And then at 325 Kelvin, it suddenly jumps up. Or over a couple of time steps, jumps up to a higher plateau. The higher plateau is reached at around 375 Kelvin. What do you reckon happens to water between 325 and 375 Kelvin? Well, it boils. This is a lower boiling point than you'd expect. This can be due to a couple of things, one of which is probably that your simulation is just so quick that it doesn't have time to stabilize properly. The second one is the simulation box is quite small. We've only got 2,500 particles. And a couple of other things. So actually, as a first approximation to where water boils, this isn't bad from a simulation point of view. Another thing that might be in effect is another thing that might be in effect here is that you are increasing suddenly the temperature by 25 degrees every step. When you boil something, you don't suddenly instantaneously kick all of the atoms so that they're going 25 degrees faster. When you boil something in real life, it's a slow process. There's diffusion of heat and things like that in play, which here is not the case. Essentially, you're saying, this is what my simulation was like at the end of last simulation run. Let's yank the temperature up by 25K, kick all of those atoms so that they go a bit faster. What happens? Oh, look, it does that. So it's not too realistic. You'd probably get a more realistic curve if you used smaller steps. Probably if you if you concentrated in this region and kicked it by like 5 or 10K per over this 50 Kelvin region, you'd probably get a smoother curve. It still probably wouldn't boil at the right temperature, but not far off. So yeah, this is a first approximation. The other cool one to look at is for enthalpy, which should look similar if I remember correctly. Oh yeah, it's because it's negative. Let's unset log scale. There we go. So the enthalpy again is increasing linearly and then increases non-linearly and then starts increasing linearly again, as you'd expect when something is melting. So that's the first thing you can look at. And the second thing that I mentioned you could look at is the radial distribution functions. I'll plot those as well. Give me a sec. For each simulation run, LAMMPS, or the LAMMPS input script, asks for a radial distribution function to be output. Cool. And the radial distribution functions that are output are the oxygen-oxygen radial distribution functions, i.e. they tell you how likely you are to find one oxygen at some distance, radial distance, or away from another oxygen, compared to how many you'd expect to find if everything was completely evenly distributed. Yeah. I've not actually looked at these in a while, so hopefully they don't look too shabby. And there we go. That's quite noisy for that. But yeah, that sort of shows us what you'd expect. For the oxygens, the 275K, so when it's definitely a liquid, is the red curve, and you get what you'd expect at a distance of. Let's reset the. From label to. So at a distance in angstroms of about 3, bearing in mind that our radius for our oxygen is, from memory, I'll look it up, but from memory it's about 1.2, 1.3 angstrom. So at a distance of about 3 angstroms, you get a peak, which means that there's well, first of all, you get below 3, you get no no frequency, i.e. there are no instances of water particles being this close to one another, as in this region of one another. And then you get a peak, which is the first ring past repulsion, and then you get a trough, and then you get a smaller peak and a trough, and it keeps going. And then if you look and compare that with the 450K, at 450K you get a high peak that then, if you forget the noise or look past the noise, you get a high peak that exponentially decays towards 1, which is typical of a gas. The reason that the peak is so noisy is because, well, frankly, it's because our volumes increase so much. So the probability of finding a particle at these distances is much smaller than in water because you've got less particles. Particles are less frequent, but compared to if they were entirely evenly distributed, i.e. instead of having point particles, if you had just a smooth particle mixture that was the average of everything, you still get a hell of a lot more particles than you'd expect here. The last question I've not looked at, but the last question I want that I asked you guys to consider for this bit, for this exercise is was to do with the quick heating effect. So I've mentioned already that here we're quickly heating something. I mean, already we're heating something by 150 to 175K in less than a nanosecond, but also every time step we are instantaneously, at the click of a finger, increasing our temperature by 25K between the end of one simulation run and the start of the next. The last question that I asked was, well, what happens if instead of using the restart file from the closest lower temperature, what happens if we use always starting lower temperature? And I've not looked at the results for that. I'm not sure what they would be. I don't know if they'd be better or worse. If anyone has, please do share them. But I think that's quite an interesting, fun question. And yeah. Are there any questions with this exercise or any other exercises? Cool. And have you guys been finding the exercises helpful at all? Or like, are there things I could change to make them better? Or are they like, do they highlight the bits that I've been trying to? Cool. Good, good. Awesome. Well, I'll stick around and answer any questions that come up in the chat in the next probably 40 minutes. I don't think I'll do anything live or at least recording worthy for those next 40 minutes. But if anyone's got any questions between now and 5, I'm more than happy to answer them in the chat. Otherwise, you can always also email me. If you email training@epcc.ed.ac.uk, I'll write that in the chat. The emails will reach me eventually. And I'm more than happy to answer them. I'm probably, I will happily answer questions which I know the answer to. I know some about LAMMPS. I'm certainly not the best person for all your LAMMPS queries, but I can answer some of them. And definitely, if you've ever got questions about Archer, you can also ask at, there's loads of ways to get support for Archer. Other than that, thank you all for coming to this session. Please feel free to stick around and ask questions for the next 40 minutes if you want. And otherwise, thanks for spending your bank holiday with us.